box. I thought I had the most sophisticated, the most fantastic ROV ever entered in this competition. It not only had 4 redundant power supplies, which you could run on any one, it had spare thrusters, it had spare electronics, it had 4 separate ballast containers that could be programmed individually to control side to side, forward and backward, as well as neutral buoyancy, or grab a very heavy object and do a dead lift off the surface, up to the surface. But it never quite worked, and I could never get the computer to control it. Still working on the software in that part. So I said, let's try the exact opposite. Let's try and throw out as many assumptions as is possible. And the very first one is, does a DC motor have to be dry? The answer is no. These little cheap $1.50 dime store brushed DC motors work fine in water, in sink water, in pool water. They work okay. They spin. Not as fast because propellers are pushing against a lot more material, but just the same. And you take them out of the water and they keep on spinning, and you set them aside for a day and you come back and do it again, and it works day after day. Why? Because the brushes keep on pushing off the corrosion. They will die eventually. It's not a long-term solution. But the competition is 30 minutes. The idea is to elegantly do the competition, not some big, grandiose outside scheme. So, throw away all those watertight containers. Everybody, almost, uses the same motors, the same bilge pump cartridge motors, because they come pre-waterproofed. No need to get any motor you like, any DC motor. You can probably work on the stepper motors and the brushless DC motors too, but the brushed DC motors, cheap, common, everywhere, in various power and size ranges, trivial to work with. Batteries. Batteries work underwater, but after a while, start to corrode underwater. I put just a little plastic container, 3 AA batteries, and hours later there was a brown film all the way around it, and they'd all corroded. So batteries can't really stay in the water. So, round 1, cast in acrylic or fiberglass, with just the power leads coming out, going immediately to inline fuse holders. But it seemed like they were self-discharging. And I know that the polymerization process pushes out all the stuff that doesn't polymerize, which might be pushing electrolytes out of the solids and into the surfaces, which is exactly where the batteries are soldered to each other, and may have created film around the batteries and allowed them to self-discharge. With time, that seems to have gone away. So this does seem to be an acceptable approach. But I thought I would try to solve that, and so I discovered that these tubes are a bit wasteful for single AA, way too small for 2. A 2.5 centimeter tube has room for about 1.9, maybe 1.8 diameters of AA batteries. Not quite enough. But if you heat treat it, squash it and make it an oval, now you can just fit 2 AA holders, 2 AA's side by side, and a 4 AA holder down the length. Now you can't use the standard end caps. So I cut my own ovals so they fit inside, so they had pressure sealing instead of just sticking on the end where it could fall off. And 2 wires coming out that I then worked on sealing. I later came to the realization that normally I worry about water pressure at depth pushing between the insulation and the wire, especially in stranded wire, and entering an otherwise waterproof area. But the power couplings always go to another wire and a heat shrink. And once I found the really nifty heat shrink at Digi, 3-to-1 shrinkage, and generates a adhesive, it seals up, and now it's the next wire's problem. And you can connect that way all the way across. So go ahead and have insulation coming out, which is then easier for the plastic to make a watertight seal. But $1.90 4 battery holders, they don't stand up to it. 6 out of 8 failed. And then I had to pull the end cap off again, tried to pull under a lot of tension. We're out, resolder the batteries together, drop them in nicely, and redo it. So I'm still doing that. This is the prototype, by the way, and is, as a prototype, very ugly. Part of the idea was to greatly simplify things. The next thing I reasoned and didn't have time to check is, does the electronics have to be watertight? Every team I've seen is struggling vainly in order to keep the last drip of water out of their electronic enclosure. Is that really necessary? Well, the Atmel chip sources and sinks 20 milliamps on every single pin as an I/O. Compared to pool water is nothing. The Atmel chip works fine. The motor driver chips take PWM signals at plus or minus 20 milliamps and generate several amp signals to drive the motors. No problem there. Camera electronics. The cheap load cameras, the board cameras, that have a 1" by 1" PCB behind them, they have a lot of surface mount. It turns out to be low current surface mount. But they do short out immediately in any water. So you cast the electronics in acrylic. And suddenly, you can take a camera without anything in front of it, just the standard optics that it came with, plop it into a cup of water, and it's blurry, but it works. And you can refocus it so that it's in focus in the water and blurry out of the water. If you go to depth, water will find the way. It was never intended to be pressure tight, so the water seeps in through the joints. And when you seal up the joints, whatever you use to seal it up with has a tendency to outgas just a little bit and fog up the optics. So we're back to having a watertight compartment around the optics and a watertight compartment around the batteries. And everything else wet, fully exposed, no protection. The LEDs, 200 milliamps, nothing compared to water. So when I first put this into the water to see how it did, and it's not yet neutrally buoyant, so it went down, and flicked the power switch on, the first thing it did was to start bubbling. AA batteries are enough to hydrolyze water. Heat tab on the 5-volt regulator that converts the 10 volts for the motors and the lights down to 5 volts for logic. That bubbled like mad. It's a different electron, so it has a little bit of advantage over the rest of it. And on the bottom side, the prototype was made by hand with printer transfer PC board etching techniques with